All right, hello and welcome back. I'm here with my co-organizer Chris, and we'd like to welcome you to the first track of talks for today. First up, before we get on to our first speaker, I just want to remind everyone to join in on the conversation over at Slack. So that is slack.cncf.io. And if you're listening today and you haven't registered and you want to get your hands on some swag, head over to kcduk.io and you can register there. It's not too late. And with all that out the way, I'd like to hand over to our first speaker for this track. His name is Joseph Irving. Joseph is a member of the team over at RVU, and today he's going to be let me double check. Talking about multi-cluster networking with Cilium and friends. So let's hand over to Joseph.
Hello everyone. Nice to be here. Let me just share my screen. Okay, that should be visible for you all, I believe. Cool. Hi, I'm Joseph. I work over at RVU. If you're not familiar with RVU, it's kind of a collection of leading comparison services across Europe. So we've got like Uswitch.com, Confused in the UK, and then we've got brands like Rastreator in Spain and Lalonx in France. All of which, compare energy, broadband, those kind of things. And today I'm going to be talking about our journey through the realms of multi-cluster networking, an area which has a lot of options in it, and still I wouldn't say a clearly defined path of what most people should do necessarily. So I thought I would at least share with you what we've done and what's worked for us or what hasn't worked for us in some cases. So to give a bit of context, I work in a team known as Airship. We provide a platform for the developers that work at RVU. We build out common infrastructure, common tooling, that kind of thing, to take away the management from teams so they can focus on actually, developing websites and stuff, not worrying about machines or patching or how am I going to get metrics, how am I going to get logs, etc. That's kind of our job to do that. However, things weren't always this way. Back in the older days of RVU, all the teams used to run their own infrastructure themselves, which was a mix of all sorts, primarily running in AWS, but some would just be standard EC2 machines. It might be like ECS clusters. We were all using Puppet, Ansible to provision machines, etc. It was up to the individual teams. And we decided as an organization, it would be more valuable if we consolidated on one platform instead of having all these teams managing themselves, which is where my team was formed. So slowly over time, we moved everyone over to a set of Kubernetes clusters as the kind of base infrastructure. But when this happened, this created a slightly new dynamic that was new to the company of we're now all running on this shared infrastructure and we don't necessarily have control over it. And what happens when inevitably, that infrastructure breaks, right? That was a big worry of what happens if a Kubernetes cluster goes down. Yeah, we have multiple Kubernetes clusters, but how do we cope with one of them or two of them going down? So we needed a way to route traffic between the clusters in an event of a failure, especially for our most important apps that make the most money on our websites. So we needed something to sit in front of Kubernetes to do this for us. And one of the first things we found while looking around was a project called Envoy. This is a project by Lyft. It's a CNCF graduated project, and it does all the kind of things you'd expect from a modern proxy. It's lightweight, it can do health checks, retries, load balancing, etc. One of the things we were particularly interested in was its ability to do dynamic configuration. So it has an API, which you typically communicate with via gRPC, and you can use this to load config into it in a very dynamic fashion. So these all seem like good attributes for a proxy to solve this problem for us. So our first pass of what this looked like looks roughly like this. So we had a Envoy cluster. It's like a cluster of nodes, but we had a Envoy sat in front of our Kubernetes clusters. and it had some configuration in it which told it which service was running in which cluster effectively. So it knew that our main energy comparison service was running in one cluster or maybe two clusters, whereas our credit card service was running in the other two clusters. And it would have this configuration, so it knew where to route the traffic when it came in. It would also, handle health failures. So if one of the clusters was down, it could route the traffic to a cluster that is still healthy. So this gave some benefit straight away. However, the main downside we had of this setup was that the Envoy configuration was static. It was completely static. It was a giant YAML file that we had full of Envoy configuration, which I don't know if you've looked at is not the most attractive to write yourself. But if a developer wanted to add a new service, or if they wanted to change what cluster their service was running in, or say it's now running in 3 clusters or whatever, they had to raise a PR, we had to redeploy the infrastructure and whatnot. So it wasn't the most easy thing to do. So we thought there must be a better solution to this. We alluded to earlier there's dynamic configuration, but how do we get this configuration? And we looked at the Ingress object that already exists in the cluster as a source of inspiration. So on the left, we have an Ingress resource. It's a kind of standard generic one. It's an Ingress. It has a host and a port, and the status, which is normally added by your cloud provider or whatever's doing Ingress behind the scenes, which includes the kind of address of what things should hit the Ingress on. And if you look on the right, we have a small snippet of a much larger Envoy configuration. And you'll find there's a lot of there's a crossover, right? There's some things that you need are clearly the same in both. Like, for example, all Envoy really needs to know about is what host names do I need to look for and where should I be forwarding this traffic to? Which is, like in our case, as running an AWS, is going to be some AWS load balancers, which are sitting in front of our clusters. So we had the information already in the clusters. Envoy just needed that information. So how do we give it to it? And that's where we built our own thing, as there didn't seem to be anything that did this for us. So we built a tool. It's called Yggdrasil, after the Norse tree of life that connects the many realms. We have a Norse naming convention. Please look up Norse mythology if you want to work here. But we built this. It's open source on GitHub if you want to peruse it at your own leisure. It's just built in Go, and it acts as a kind of mix of a controller, and it's a mix of like a Kubernetes controller and an Envoy control plane. So what it does is it goes and watches various Kubernetes clusters for Ingress resources, and based off these Ingress resources, it translates that into Envoy configuration and sends it over to our Envoy cluster. So, for example, if you have an Ingress in one cluster, Yggdrasil will pick that up and configure Envoy to route there. If you had the Ingress in 2 clusters, it would see the same Ingresses in 2 clusters and configure Envoy to route to either of those clusters. So this was a nice and easy way to allow people to kind of get the benefits of Envoy without really needing to even know about it. Because from all the developers' perspective is they just create an Ingress object in one cluster, they create another cluster, Envoy does the rest, right? It all gets configured for them. They don't need to worry about that detail. They just use Ingress, which is a fairly common standard object that everyone's familiar with. And it gave us the advantage of, if a cluster goes down, for example, it will, as alluded to, it will route the traffic to the ones that are working based off health checks and whatnot. So this was a good like first start, some reliability, I guess, for our clusters, especially in the early days of using Kubernetes. This was more frequent than we might want it. But what we realized we had done here was we had accidentally created some kind of service mesh. It soon became apparent to our developers that instead of going between clusters, going through Envoy was a very efficient or easy way to connect to our internal services so that they could talk to each other. And this started to become a de facto way of kind of cross-cluster communication, was to go through Envoy, because it always knows where the service is, and it will always route you to where it's healthy. So this is a kind of like slightly zoomed out, detailed look of what this might look like if we view a request. So if you first look at the black line here, this is like a standard, let's say, user request from a website. It goes through to Envoy, hits some load balancers, hits a node, it's like proxy to an Ingress pod or something, and then finally ends up in an actual, application pod that's serving the website or something. But then this pod wants to go talk to some other downstream service in our like microservice architecture, and it does the same thing all over again and would have gone and the same loop. And who knows, this pod may want to talk to some other microservice, and this loop can repeat quite a few times. So there's some obvious downsides to this. One of which is we're adding quite an extra bit of latency every time we do this. It's not the biggest latency in the world, but once you add up quite a lot of these hops, it can become significant enough to be a problem. And it's also one of the other key things is it's losing something. You're losing identity by doing this. By going out of a cluster then back into a cluster, it's hard to distinguish whether this is kind of like service to service traffic, whether it's user traffic. It's all just coming from Envoy as this load of network traffic. So if you want to use things like Kubernetes network policies, things like that, it all becomes a lot more difficult. So we had the advantage of it being easy to use, and Envoy was also doing a lot of the hard work for you, but the disadvantage of we were getting this extra latency and this lack of identity, which could make life difficult for us. So we thought we probably need a better solution for this. This wasn't the original intent of our thing, and the obvious place we looked to was some kind of service mesh, right? That service mesh can do this kind of stuff. So we started a journey of exploring a variety of the service meshes that were out and about at the time, with a few key features that we were interested in. The primary one, as is the topic of this talk, was multi-cluster services. It had to be able to do cross-cluster. That's pretty important. The second one, which was maybe a nice to have, but something we quite like, was the idea around real inverted commas pod IPs. And when I mean real, I mean the pod IP of your pods is the same, it comes from the same CIDR that your VPC is, for example. So you're not using like a virtualized network, you're using real pod IPs. And this allows you can do stuff like, it can simplify networking. You can do things like in AWS, you can do like VPC flow logs on your pods or things like this. It can make life easier. And third, and in some ways the most important, was it had to be easy to add to our existing stack. We didn't want to have to rethink how we did everything to be able to use this. This was a fairly small feature we wanted. We didn't want to have to change application code, for example, to take advantage of this feature, especially as the current way was so easy. How would we convince people to use it if the new way was much more difficult? So we went out, we reviewed a load of service meshes. I'm not going to like pick on all of them by names or anything. So, but we reviewed a load of them, and we found some common problems across the ones we did look at. A big one was it didn't support multi-cluster, especially when we looked at this. There were a number that just didn't support it. So that was a non-starter. Second was a few of them were quite complicated and had quite a lot of additional features we weren't interested in. They were doing a lot, whereas we needed only a fairly specific thing. And the added overhead of operating these service meshes didn't seem worth it compared to what we were actually after. And the third one was often they seem to require changes to how you consider architecting your applications or your clusters or whatnot. And it seemed like it was going to be too much work involved in actually changing them. Worth noting, some of these might be slightly different in present day, as this was a little while ago, but I think a lot of these cases are still somewhat true. And another big one, which I don't mention on the next slide, was the problem we had with sidecars. So sidecars are a common pattern for service meshes, which is you have your standard pod, you have your application containers in said pod, and we have a sidecar container that runs alongside this that does all the networking stuff. So it often might terminate TLS, it does the service discovery, etc. But there were a few key problems with this. that stopped us from progressing much further. One of which is they didn't work in the init phase. If you have init containers, they wouldn't be able to use a sidecar container. There's often complications around startup shutdown of your pod. Let's say your application containers start up before your sidecar containers. You might have some strange network shenanigans going on. We lose quite a lot of cron jobs cluster in our clusters, and we found that they would forever hang because the sidecars wouldn't know to terminate when the job was finished. Now, these are all generic problems to sidecars that a lot of service meshes that use this kind of approach have. And I know over the years there have been more and more workarounds to fix some of these problems. But they do cause complications and don't work in every scenario. So we found this to be slightly undesirable at the time. So after looking through all of these, we found a new project that we were familiar with, but seemed to fix a lot of our things, and that was Cilium. So Cilium, developed primarily by a team called Isovalent, currently is in the process of becoming a CNCF project. Still in voting, I believe, so I won't preempt the result. But yeah, it should be a CNCF incubator project soon, hopefully. And that's key things we liked a lot. One was it ran as a daemon set. It's not a traditional service mesh. It's more of a CNI, I would describe it as. But it runs as a daemon set on all your nodes, so it doesn't need to go into the actual pods of your applications. It's just running on each node. It supported real IPs. It does that using AWS Elastic Network interfaces in AWS specifically. It does also support them in other clouds. I'll talk about that in a sec. Has a feature called cluster mesh, which was the the main thing we wanted. The cluster mesh is a way of networking between Kubernetes clusters using Cilium. And maybe just a cool thing, but it also does everything using technology called eBPF. Now, I'm not an expert on eBPF, so I am not going to spend much time talking about how it works in this presentation, though there is a presentation tomorrow about that by Josh, I believe. So please tune into that if you want to know more about eBPF. But it's a very cool new networking technology which writes rules directly to the kernel instead of like IP tables, which is quite the standard way a lot of Kubernetes stuff would have done it in the past. And last and probably most importantly was it didn't require any application changes to use any of these features. We could deploy this and just start taking advantage of all of its features. So now I'm just going to quickly go over how it works from again high level. So starting off with IP allocation. So how does it give our pods real IPs? And it does it in a fairly elegant way, similar, by the way, to the AWS VPC CNI, if you're familiar with AWS's solution. But effectively, Cilium just allocates real IPs from your CIDR to an elastic network interface on your node. If you get a pod, it will just give the pod an IP and then allocate that to your Elastic Network interface at the same time. So it's all a real AWS IP that you can use in your clusters. That was straight away nice. Mostly a nice do some kind of IP allocation, but yeah, this is how Cilium does it specifically. But more interesting perhaps was how it handles services. So on the left here, we've got a Kubernetes node and Cilium's running on it. And on the right here, we've got just a standard kind of generic service in Kubernetes where you have a name and you have like a cluster IP. It's a pretty standard way of doing a service in Kube. And you have two pods that are associated with that service. They match its selectors, etc. And then what Cilium does behind the scenes, slightly simplified, but what it's doing is it's writing some BPF rules which associate that cluster IP, which is just a virtual fake IP, with those pod IPs, and it's writing them into the kernel, in which case the two pods shown here, similar to what kind of like kube proxy does with IP tables. And that's how it just works for standard service. Simple, not much, nothing too crazy here. But what you can then do with Cilium is you can expand this to cover multiple clusters. So if I have the same service in cluster A, let's say, and then the service again in cluster B, Cilium will realize it's the same service in both clusters and will just compile the rules to forward to any of the IPs, regardless of what cluster they're in. So you just get this list of rules if it can hit any of these. So whether it be in cluster A or cluster B, it's available to you. Also, this is working off of a service. If the pods aren't ready or not, they won't come up as ready endpoints and wouldn't be added to this list. So That's a nice bonus of that. But yeah, and this is very simple because it means you're not, there's no complicated shenanigans going on from your app's perspective. It just hits the service as it would normally, and it now has just more options of where to go. Right, it can now go to a different cluster as long as that IP address, is routable and whatnot to that pod. It will just go there. We're just talking pod IPs to pod IPs here, which are just real IPs in our case. And the question is, how do you turn this on? And this is what's the best part about Cilium is this is a normal service definition in Kubernetes. And the only thing that's different about this service, which is a Cilium service that can go across cluster, is this annotation here. You just add an annotation of a Cilium global service true, and this was enabled for your service. You do that, and you need to ensure that the service is deployed in any cluster which you want to access the service from as well, because you need the kind of address for your pods to hit. But as long as this service exists in the clusters you need to access it from, and it has this annotation, it works. Well, no, you don't have to have any pods behind the service. So you can deploy the service in a cluster with no pods that match it. And that would just allow other pods in that cluster to hit that service and get routed to some cluster where those pods did exist. That's effectively how it works. Yeah, so that gave us a easy way of doing some cross-cluster communication. And so this is a simplified diagram of what we had earlier, which is the new journey of we just go from one pod and it just directly talks to another pod. There's no going around in and out, etc. It is literally just talking from one IP address to another IP address. And it does it all kind of without even needing to know what's going on. So that was how we solve that problem. And as well, not only are we avoiding this latency add, for example, by going in and out, we're now doing it from pod to pod, and Cilium is aware of what pods are talking to what pods. We are still maintaining all the pod identity in this scenario. So if we want to apply security rules from like network policy and stuff, it all works. We can use our pods, labels, services, etc. For this to work, which is nice if you need to do that kind of thing. Now, we found once we'd done this, it started to become very easy to link an arbitrary number of Kubernetes clusters together as well. We're primarily in AWS, so something we took advantage of, which we hadn't used before, was AWS's transit gateway feature. For those not familiar, transit gateway effectively allows you to simplify peering connections between VPCs significantly. Whereas in a traditional AWS setup, you might have had to peer all your clusters together in this kind of complicated web of peering connections. With a transit gateway, you just add that to each VPC, and then it works like a hub and spoke in that network traffic can just flow from one cluster to another cluster and vice versa, as long as the route tables, security group rules, etc. are set up correctly. This should just work. So if we wanted to create a new cluster and add it to the mesh, we just spin it up, attach it to the transit gateway, and tell Cilium about it, and then the networking just works. So this was nice and easy, much preferable to peering connections if you have done a lot of those in the past. And we found this works quite easily as well between different clouds. So we also have some stuff running in Google Cloud, primarily some of our data stuff runs in GCP and GKE. We do a lot of stuff with BigQuery and whatnot. So we do have some clusters over there. And just by connecting the two clouds together, which in our case, we just connected them via a VPN to our transit gateway, and using a transit VPN on the GCP side, we could easily share network connectivity between them in a secure fashion. And Cilium, again, just works. We have Cilium deployed on our GKE clusters. It also uses native IP addresses in our GKE clusters, and allows you to hit services in our EKS clusters just as easily as you would if you were in AWS, right? You're hitting a service. It does not make any difference what cloud you're in as far as this is concerned. So so you can do this to, I guess, an arbitrary number of clouds. So it works very nicely and easily. So yeah, that was kind of our general networking setup that we've done with Cilium. Are there any downsides to this approach is one question though. And the first one we hit quite quickly, I guess, was that it does use eBPF as its primary way of doing stuff. And when things go wrong with eBPF, it can be tough, especially for someone like me, to debug what's going on, compared to the more like vanilla ways that traditional service meshes do it. You might need to learn some new skills to debug some of these issues. I will. Well, I must say it was more when we were starting that we did hit issues. We don't really have issues with Cilium anymore. And I would also add that the Cilium community are like amazing. Like if you go on the Cilium Slack and say to them, my thing doesn't work, they will spend way more time than I would have thought trying to help you debug it. I've spent many hours, literally hours with them, sending them debug logs and things. And so they're very, very helpful. And very nice as a community. Never had that kind of service. So they're very impressed with Cilium on that path. And then the second one was more about the kind of missing link, I guess, is still around, like with our old setup, we went through Envoy and we got all the benefits of like health checks and retries and it's doing its load balancing and whatnot. And by going pod to pod, you do lose a bit of that, right? You're just doing simple, basic kind of like round robin style load balancing, but there's no retries or anything built into Cilium. It's just doing IP to IP. So your apps will need to implement some kind of retry logic or stuff like that if you need it. That is a downside of this approach. Though some might say it's a plus side, like there are arguments to be had for it's better to have this kind of logic in an app, but it's things you can work around. But yeah, it's something it doesn't support, at least out of the box. Some like future of this is while we have basically only just scratched the surface of what Cilium can do. It does a lot of stuff. There always seem to be adding new features to it. It can completely replace kubeproxy these days, which is pretty cool. It has this amazing graphical UI called Hubble, which can show you all sorts of nice networking data visualizations, what's going on in your clusters. They've done like IPsec using Cilium now exists. So again, we barely even started to take full advantage of all the stuff it's delivering, which is pretty exciting. And just as a note, it can be ran with other service meshes as well. For example, if you want to use a kind of sidecar approach service mesh, Cilium works just fine with that. It has no problem working in tandem with these things. In fact, it has some guides on their website for doing those if you want to. So yeah, it's not a problem if you do further down the line. If we do decide we need something more traditional, I don't know, if we want to do some kind of like TLS, mutual TLS style setup, or if we're trying to do retries generically, maybe we will look into a service mesh, but it's not an issue for our organization, at least, but it can be done. So yeah, and then that brings me kind of to the end of this talk. If you got any questions, please let me know. You can contact me on Twitter, and there's the KCD Slack channels on CNCF Slack, where I'll be happy to answer any other questions. Hopefully this gave you at least gave you one story of how people are solving this problem. As like I said, I still think it's a very open question of how to easily mesh together different clusters. So this was one example of it. I'm sure there's many others, and I look forward to when someone does settle on what's the best one. But for now, it's works for us. Thank you.
Thank you so much, Joseph. That was brilliant. We do have one question, if you don't mind answering that, over in the Slack channel. If you like to answer it now, I can say it out loud, or you can pop over there.
Sure, you got to ask it now.
Are you using Cilium with the Amazon VPC CNI or as a replacement?
Both. Originally, we used it with the AWS VPC CNI, as that was the only way of doing it. So we chain it with it used to be chained. So the VPC CNI would do the ENI allocation, and then Cilium would do the rest. But these days, it can be used as a complete replacement, which is where we're using it in our newer clusters. Yeah.
Brilliant. All right. Well, that's all we had. Thank you again for your time, and I'm sure that if there are any other questions that pop up, they'll be in that Slack channel. So thanks again for that.
Yeah, feel free to jump into the Slack and interact with Joseph. I know he'll be around and be keen to answer questions.
Amazing. And on that note, I'm going to hand over to Chris to introduce our next speaker.